One of our students, Josh, one day was idly spinning these plastic jacks for uh, playing the game pickup jacks, and he observed something that sparked his curiosity. And let me play this movie here to illustrate for you exactly what this was. See if you can see it. Okay, now what you saw there was that as the jack was spinning, it sort of appeared to slow down and stop and then go backwards. Let me play it again. And I'll play it one more time. So he was doing this at his desk, Josh was, and he saw this and he says, why is this happening? So some of you may have seen the same effect in watching old movies with the stagecoaches, and you watch the wagon wheels, and the wagon wheels appear to do the same thing, in that they appear to slow down, stop, and maybe move backwards. It's a very similar effect related to that, but at the same time, it's just different enough that it might take a little bit of thought to figure out what's happening. So with that, let me move this movie out of the way. Okay, now let's look at this still photo of the jack right here. Okay, now let's imagine that the jack is spinning around in this direction, like that. Now I've drawn this axis right in here because I'm going to use this to explain a little bit about what we're going to do. And that I say imagine as the jack is spinning like this, okay, it moves in this direction. Now how do we measure the motion of the jack? Well, we're going to look at the angle, let's say, that this arm of the jack makes with this horizontal axis. Okay, and I'm going to say, suppose that this jack moves at a speed of 1 radian a second. So 1 radian might be something like that. So every second it moves that far, okay, and so on. Now, so the speed of the jack in terms of angle per second is 1 radian per second. And we're going to multiply that 1 radian per second by the amount of time that it spins, and that tells us exactly how many radians this arm of the jack has moved in that time period t. So W is called angular velocity, and it's a very important and widely used concept across science and engineering. W is the angular velocity with which the jack spins. So the jack spins at an angular velocity of omega, whatever that happens to be. If I call it W, it's really typically used the Greek letter omega, small omega. And so let's imagine that this jack is spinning around with that angular velocity omega, and in one period it will spin all the way around and come back exactly to the starting point right here. In 2 periods it spins all the way around and comes exactly back to that starting point. That's assuming that the angular velocity doesn't change. It's spinning at the same speed. So now, as this thing is spinning and we watch it spin, it'll appear to be a blur because our eyes are just not quick enough. We don't have enough time resolution in our vision to be able to actually track the motion of this individual arm of the jack. Okay, so it just appears to be a blur. But suppose that once every revolution around, we were spinning the jack in a dark room, and once every revolution around, a strobe light goes off. Boom, there's just a bright flash of light. So for that instant in time, we see the position of this arm of the jack, and it's right here. Okay, it spins all the way around again, and the strobe light goes off again, and we see the position of the arm in exactly the same spot. So if this jack is spinning pretty fast, let's say it's going 20 or 30 revolutions per second, and we have a strobe light going off at exactly the same rate at once every revolution, then when we look at this jack, it'll appear to us as to have not moved at all between the flashes of the strobe light. It will appear to be not spinning. Okay, now what happens if the jack is spinning just a little bit faster than when the strobe light goes off? So the strobe light goes off first time when it's here, then it spins around, and instead of being here, it's up here a little bit, and the strobe light goes off. Okay, then it spins around, and instead of being here, it's up here a little bit, and the strobe light goes off. If that happens, then the jack will appear to be very slowly spinning in this direction. Okay? What happens if the jack is spinning a little bit more slowly than the period of the strobe light would indicate, so that it starts off here, the strobe light goes off, but it doesn't quite make it all the way around. The jack is now positioned here when the strobe light goes off. Okay, then it spins around, doesn't quite make it all the way around, so that it's now positioned here, and the strobe light goes off. In that case, the jack will appear to be spinning backwards. So it depends on the relationship between the time period of revolution of the jack and the period with which the strobe light flashes. So, but he's just sitting at his desk spinning this jack. There's no strobe light. So why does he see this effect where the jack appears to be slowing down and perhaps stopping and then going backwards? Well, there is a strobe light. In that there are fluorescent lights in this classroom. Now, a fluorescent light, let me show you here. A fluorescent light actually flashes 120 times a second. Well, how is that the case? How does that happen? Well, let's look at it like this. We know, or maybe we don't, that the electricity in the plug in your house or in your office or in your school oscillates like a sine wave. It goes like this. So not a good drawing. Okay, and the period between peaks in the sine wave is 1/60th of a second. Okay, so this is 60 cycles a second is what the period of your house current is. 60 times a second, it has a sine wave that goes through one period. Now, the fluorescent light, okay, is hooked right up to this oscillating sine wave house current, and the fluorescent light flashes bright when the voltage is at its maximum up here, and when the voltage is at its negative maximum down here. Okay, so if you have 110, 120 volt, depending on how they measure it, it will only flash in that region right there. Oh, I didn't mean to do that. Well, maybe I did. That's okay. So what we have then is that, okay, here's our sine wave. So the strobe light will flash, and oh, my mouse disconnected here. Let me connect it again. The strobe light flashes, let's say, right in this region, right in here. Okay, so when the voltage is right in that region, it flashes. When the voltage is in this region, right here, it flashes. Okay, so it flashes twice in 1/60 in one cycle. So if the cycles are at 60 cycles a second, the strobe of the fluorescent light will flash at 120 cycles per second. So indeed, when you have fluorescent lights, you will see a strobe effect. Now, if Josh takes his jack, as was suggested, and he goes outside of the sunlight and spins it, he doesn't see that effect. If he spins it under an incandescent lamp, which doesn't have the strobe effect, he doesn't see that effect. Okay? The effect of it slowing down, stopping, and going backwards. So, now, let's, with that as a physical explanation, let's look a little bit at the math of what's happening. Okay, and for doing that, I use Excel. So let me pull up Excel right here. Okay, now let me tell you what I'm doing. In this column right here, I'm using that to represent, let's say, the x-axis. On that, remember, I drew the. I said that the angle is equal to omega t. Well, think of it as omega t equal to x. So I'm putting down the value of omega t. So this is giving me the angle location of the spinning of the jack. So here we start the jack off where the angle with the x-axis is 0. Then I'm going to evaluate it when the angle of the x-axis is 1/10 radian. This is in radians, not in degrees. Here the angle of the x-axis is 2/10 radians, 3/10 radians, and so on. So here I'm representing the angle that the arm of the jack makes with the x-axis in radians. Okay? Now over here in this column, what I'm doing is I am going to compute the cosine of that angle. I start off saying the cosine is of the angle. Here, let me show you what I'm doing. No, I'm sorry. I said cosine, but I'm computing the sine of that angle. So whatever's in here, I compute the sine. And when that's 0, we know that the sine is 0. And that this formula, where the sine of A1, and this is the cell A1, and this is repeated all the way down. So, for example, right here, what's in this cell is the sine of A5. A5 is this. Now, if you're not quite familiar with how to use Excel, what you do with that is, let me go back up to the top for me. Right in here, you click your cell, and you put equals, and then put sine, parentheses, A1, close parentheses, and then return. Okay, so this now computes the sine of A1. Then I drag the corner of this all the way down, excuse me, and it then puts the appropriate formula in each box. So this is the angle that the arm of the jack makes with the x-axis, and this is the sine of that angle. Okay, now over here I'm doing something just a little bit different. Here I'm imagining a situation where the frequency with which the strobe flashes is just a little bit different. So instead of the sine of A1, I'm putting the sine of A1 times 1.1. Okay, so this makes this changes. So they're not quite the same. If this was 1, then it would be the same as this, but it's not. It's 1.1. So this angle that we're putting in, A1 times 1.1, and taking the sine of it, this angle is changing just a little bit faster than this angle. So it's the effect of the strobe not going off at exactly the same time as the spinning jack. Okay, so the strobe will complete its full 2 pi circuit, if you like, just a little bit more quickly here. So I've drawn a graph of these two sine waves. Okay, we have one, the blue line is the graph of the arm of the spinning jack. So it says the spinning jack starts off at 0. 1 cycle later, it's right here. It's the red line. Okay, 1 cycle later, it's right here. 1 cycle later, it's right there, and so on. So the red line represents the sine of the angle of the spinning jack. The blue line represents, the red line is the sine of the angle of the strobe. The blue line is the sine of the angle of the spinning jack. So let me say this again. I apologize for the misstatement. The blue line is the sine of the angle of the spinning jack. Okay. The red line has a little bit higher cycle, of course, shorter cycle. It's a higher frequency. And the red line goes through 1 cycle just a little bit more quickly, as I explained. So we have the blue cycle and the red cycle. So imagine when the blue is right here, is when the jack has finished 1 complete cycle. Here the strobe goes off a little bit faster. Okay, so just before the jack completes 1 complete cycle. So the red line and the blue line don't quite line up. The strobe goes off just a little bit before the jack completes its circuit. Okay, and then the next time it goes off, it's a little bit before that and a little bit before that. So if the jack is not quite getting all the way around, this means that the jack would appear to be going backwards. But what do we see? Okay, what do we see? Well, what we see is, imagine that the jack is spinning and our strobe is going off. And we see the light from the strobe bouncing off of the jack and coming back. So that's what we see. So to represent that mathematically, I multiply the sine wave of the strobe, which is when the light's getting bright and dim. Okay, so imagine the strobe is bright here and it's dim now down here. So we only see the jack when the strobe is bright. So we see then that we explain physically that this jack will appear to be moving backwards. What our eye sees is the product of the strobe flash times the position of the jack. So here's the next thing, which is really interesting, and that is what I have in my column right here. Okay, and what I'm computing right here in this column. Okay, here's the angle of the jack. Here's the angle of the spinning jack. Here's the angle of the flash of the strobe. And in this column, what I'm computing is I'm computing the product of what's in this column times what's in this column. So the product of the two, which I just explained, is what our eye sees. It's what we get when we multiply the intensity of the flashing light times the image of the spinning jack. Okay, so this is what we see. So I multiply these two together. Now let me plot, excuse me again, let me plot all of these different sets of numbers. Okay, the first one, as I said, the blue line is when the spinning jack, the angle on the spinning jack, and we can see that it returns every 2 pi back to its original position. The red line is when the strobe goes off. Okay, it's going off a little bit before the spinning jack gets all the way around. And then this is our product of the two. So what we see here is this really rapidly varying sine wave. And then we see this overlaid, slowly varying sine wave. So what we look at, the product of these two sine waves, our eye sees a function that looks something like this. However, this rapidly varying sine wave is too fast for our eye to respond. It turns out that this rapidly varying wave is about twice the frequency of the spinning jack and the flashing strobe. Now, if you think about it, with fluorescent lights, we can't see the strobe flashing because it flashes so fast for us, and we also can't resolve the absolute position of the jack when it's spinning because it's going too fast. So this is twice the frequency there, and this then is, now these two graphs are not on the same x-axis, if you notice. This goes all the way up to 30, this goes up to 120. So you can't look at this variation and compare it directly with this. You have to look at the angle on the x-axis here. But this is varying way too fast for our eye to see. We don't see that. But what our eye does see is it sees this right here. So as we're watching it spinning, we see this much more slowly varying sine wave. We don't see this rapid variation. So this is what gives us the sense that the jack is somehow not spinning quickly. It could either appear to be stopped completely, in which case there would be no sine wave here at all, or it could be spinning just a little bit more, going a little bit backwards or going up a little bit forwards, and that'll be determined by whether by the frequency on this larger sine wave. What this larger sine wave is right here is it's actually the difference in the frequencies of the red and blue sine wave up here. Now, I could write out the math on that, the trigonometry, but I'm trying to explain this to some junior high students, so they're not really quite ready yet to discuss the trigonometry. So I can leave that for another lesson. Okay? Until next time.